Okay, so yesterday we reached the following point. Today it will be rather technical, and but we have to go through this because it's really the core of the Dirac equation. So we wanted to know under, if you have a Lorentz transformation with coefficient, with matrix A mu, we wanted to know how the solution of the Dirac equation transform. We had not yet found, but where this is a matrix 4 by 4 that mix the four components of this tensor, of this vector, that is the solution of the Dirac equation. Remember, psi of x is always psi 1, psi 2, psi 3, psi 4. Okay? And yesterday we had found that this S, we had not found this form, but we had found that it has to satisfy the following relation. Gamma nu s to the minus 1 A equal A nu mu gamma mu. Okay, these are the gamma matrices of Dirac. This is the transformation coefficient for the Lorentz transformation at the space-time level. And basically, we are looking at the Lorentz transformation at the Hilbert space level now. Okay, well, the first things that we do is the following. We try to solve for an infinitesimal transformation. So first, infinitesimal transformation. And the infinitesimal transformation has to be this A, that is this A, okay? And so let's write the A nu mu as delta nu mu plus delta omega mu nu. So this is some unknown small quantity that depends on the parameter of the theory, and this is the identity. So as it is an infinitesimal transformation, it will be the identity plus something. So this is the object, okay? And you see these mu and nu are matrix at this level, and at this level they are matrix element. Now, how we write the S? The S we will write in the following manner. It will also be infinitesimal. So we will write it as the identity minus I for sigma alpha beta delta omega alpha beta. Now, what here yesterday I said, let's be very careful. Okay, this is a matrix 4 by 4, okay? But you see these index alpha and beta are saturated, and they are not here. They are matrix indices in the sense that these can be considered in alpha and beta a matrix. But this one instead, alpha and beta are two indexes where sigma is a matrix, of which alpha and beta are not the index, okay? So that is what I stressed yesterday. So let's parameterize S in this form. We still have to find omega AB and sigma. So this is a matrix 4 by 4. This is a matrix 4 by 4, but there are many. There are many, and they are labeled, all these matrices are labeled by alpha and beta, and they saturate with alpha and beta. This delta omega is the same as this one, but with an index pulled up via the metric. Okay? So this sigma is a set of many matrices. Each matrix is labeled by these two indexes, not the element of the matrix, okay? So here this is a number, and how many numbers I have? I have many numbers as alpha and beta, so I can organize them as a matrix. Here instead I have many matrices labeled, each of them by alpha and beta. You understand? So this I have. The matrix, for example, sigma 0, 1 is not the element 0, 1 of this object, okay? This is, it means the matrix sigma 01. So this one, sigma 01, has then his own indices, A and B, okay? O and 1 are just labels, so maybe I should put it among parentheses. If I put among parentheses, it means they don't indicate elements, but they label which matrix I want, okay? So this is very important. But now that we have parameterized in this manner, and of course you can say, how do you know that you can parameterize in this manner? Where we are doing infinitesimal transformation, so the transformation of space-time will be the identity plus a small transformation depending on the parameter. So I call this in this manner. So this is just a notation. Now we have to find the explicit form of this. And this one, this is a matrix, so it will be, is a 4×4 matrix, so it will be a matrix. It depends on A, but A carries in this information, so there must be this information coming in, and in fact is here. But then these are numbers, okay? And as this is a matrix, I have to multiply by some matrix to saturate these numbers. So this number comes from A. This delta omega comes from A. But then I have to build some matrix, so I call this matrix sigma. They have nothing to do with the Pauli matrices. We will see what they are. So our goal now is to find both omega and sigma. And we will do for some particular case. So the issue is find delta omega mu nu and sigma, let's call alpha beta, where I put the alpha and beta among the things. Well, it should not be too difficult, because we know that the S has to satisfy this relation. And this relation, you know, we derived it yesterday, imposing that the Dirac equation is invariant. Is invariant in the sense in form is invariant. X goes into X prime, psi goes into psi prime, but the form is invariant. So let's now plug in, so now let's plug in this here, and let's plug in this here and here. Okay, so we put in now this form there and there, but let me first write down this. So now on the left hand side I will write delta mu nu plus delta omega mu nu gamma mu, that is this object. So I have written, instead of writing on the right hand side, I have written this on the left hand side. It is the same. Then I have to write this object, but this object has this form, 1 minus 4 sigma alpha and so on. So I have the identity minus I for sigma alpha beta delta omega alpha beta. I have put a hat on it just to indicate that it's a matrix. These are not numbers. These are many matrices labeled by alpha and beta. There are 16 matrices labeled by alpha and beta. Okay, then we have, let's say, gamma nu, and we have I plus I4 sigma alpha and beta delta omega alpha and beta. Now, here the index mu is saturated, so this is nu mu. And the free index is ni, so this is an object that has index ni. And let's see here, all the indices are saturated, even if they belong to different spaces, and the free index is ni. I have indicated this is S of A, and this is S to the minus 1, the inverse of A, so I just put a plus here because the infinitesimal are changed only by thing. Now, let's do the product, but let's neglect the, first of all, there is a term, gamma mu times this give me gamma ni. This times this give me gamma ni, and they cancel. Then on the right-hand side, I neglect the things that are second order in delta omega, just because I don't want, they are small, so I neglect second order things. What you get is the following: delta omega mu nu del gamma mu is equal minus I4 delta omega alpha beta sigma dot alpha beta gamma nu minus gamma nu sigma alpha beta. Now, yesterday, I don't remember if we proved that these are antisymmetric. Did we prove yesterday that this is antisymmetric? Okay. Okay, let's take, eventually we will do the proof afterwards. These are antisymmetric. Then if you take account that they are antisymmetric, you can write these, okay. Let's take this equation and we can rewrite these objects. Let's rewrite this object in the following manner. Well, we just copy delta, so there is I, delta, there is something wrong with an I. The I is there. Okay, let's take this object without the I for a moment. Let's remember that this is antisymmetric, so we get, and it must be equal to this, so we have G nu sigma delta omega mu sigma gamma mu. What I have done, let me see what I have done. Let me write, then I understand. Right, but I have to leave the I there. Now let's see the position of the nu. The position of the nu is this. But this is just a delta. You see, this G with the index 1 up, 1 down is just a delta. So I have really done nothing. This is just delta mu nu, and this is delta mu nu. This is just a Dirac delta. When an index is up and one is down, this is just a Dirac delta. So I'm just rewriting that. And then I am rewriting this in this manner. I have brought this on the other side. Okay. Now this one is equal to delta omega alpha beta G nu alpha gamma beta. Okay, that is this written with different indices. Now okay, this is also equal to delta omega beta alpha G nu alpha gamma beta. Okay, I have just and the beta has to be down, sorry, beta has to be down. Okay, and this one, so I have just rearranged the index, I have done nothing, but this one, because of the antisymmetry of this, is equal to 1/2 delta omega beta alpha G nu alpha gamma beta minus G nu beta gamma alpha. Okay, because of the antisymmetry of this, I put a minus here, and I have exchanged the index. Okay, so I get this quantity, and is also equal to minus 1/2 delta omega alpha beta G mu alpha gamma beta minus G mu beta gamma alpha. Okay. Now if we compare the two, we have the same factor, omega and omega. Here we have 1/4, here we have 1/2. So comparing this term with this term, so let's compare this term with this term, and what we get is the following things. Now 2I G mu alpha gamma beta minus G mu beta gamma alpha is that object where I have brought the I on the other side, and this one is equal. So I have dropped this term, okay? I have kept the I, and I have brought a 2 up, and then what is left is this, but this is the commutator between sigma alpha beta and gamma nu, okay? So this is the result of this. Comparing this with this, you get this result, okay? So what I've done, I have inserted here the infinitesimal transformation, neglect, so here basically I have neglected the second order term in delta omega because they are very small. I go on and I get to this relation. So let me write down this relation because it's very important. What can I cancel? So basically I'm comparing this with this, okay, to get this relation. Can I cancel this? So let's write down, we have 2I G mu alpha gamma beta minus G mu beta gamma alpha equal sigma alpha beta gamma nu, and this is the commutator, so I put a minus there. So this is the relation that I have, and all on the left hand side everything is known. These are the metric, this is the gamma. What is unknown is this. So I should solve this equation. It's not easy to solve, so I'll provide to you the solution, and then we go and check that is the solution. Okay, so this is the relation that the sigma have to satisfy, and the sigma, remember, enters the S. Never lose the logic trail that we are doing, okay? The sigma is the ingredient that we need to build the S, and the S is how the wave function transforms. So we have to solve this equation. Now I will show to you which is the solution, and we will check it. We will prove that is the solution. So that was the equation that has to be satisfied. Can I cancel the rest? All the steps are also in the books, okay? Either in the form of exercise or just in the form of the lecture. So now the solution of this, the solution is the following. Sigma alpha beta operator is I over 2 gamma alpha gamma beta, the commutator. And then you see that alpha and beta, like for the gamma, they are not index indicating the elements of the matrix. They are labeling which matrix I take. So for the gamma, I have gamma 1, gamma 2, gamma 3, gamma 4. This is not a label of the index. In fact, it's only one, and it labels which matrix I am using. The same here, I have two index, but they label which matrix I have. So I have 4 here, so altogether I have 16 things. So the solution of that equation is this, but now let's prove it, okay? Now, let's insert this here, and so now we go and prove that it's a solution. It's not that I tell you, well, we found it. No, we just, I tell you which is the solution, and then check that it is really the solution, and that it is the only solution, okay? I will only check that it is a solution, but believe me that it's possible to prove in a complicated manner that is the only solution. Okay, so let's insert this expression into here. We have I over 2 gamma nu sorry, is the other way around. Is gamma nu sigma alpha beta. Whatever, there was a sign that I misplaced. So now let's insert his expression there, and I have gamma alpha, gamma beta. Okay, so I am just inserting this here and going on and calculating. So this is the sigma. I am telling you the solution is this, but now let's check if that is correct. So I am inserting this there, and I get this expression. Now let's work it out, this expression. I have I over 2 gamma nu, gamma alpha, gamma beta, gamma beta, gamma alpha. This is the commutator. Now I have to remember, of course, the well-known fact that the gamma alpha, gamma beta have the following anti-commutation rule. Okay, so now let's do these things. You get gamma nu, gamma alpha, gamma beta, minus gamma alpha, gamma beta, gamma nu. Then I have with the other one minus gamma nu, gamma beta, gamma alpha, plus gamma beta, gamma alpha, gamma nu. Now let's use the anti-commutator rule, that one, in these two pieces. And then we will get, so using the first one, I get gamma nu minus gamma beta, gamma alpha plus 2g alpha beta. Then for this I have minus gamma beta, gamma alpha plus 2g alpha beta, gamma nu. So this is this piece where I have used the anti-commutator. So gamma alpha, gamma beta, I know is equal to gamma beta, gamma alpha with a minus, and I'm adding the piece 2g alpha from that one. The same here, I turn this around, gamma beta, gamma alpha, and then I have to add plus 2g alpha beta, and then I have gamma mu. Minus gamma nu, gamma beta, gamma alpha, this piece, plus gamma beta, gamma alpha, gamma nu. So now let's work this out. I have minus gamma nu, gamma beta, gamma alpha, plus 2 gamma nu, g alpha beta, plus gamma beta, gamma alpha, gamma nu, minus 2g alpha beta, gamma nu, minus gamma nu, gamma beta, gamma alpha, that is this, plus gamma beta, gamma alpha, gamma nu. Now let's see. We have various pieces that are the same, like this one and this one, and so on. If you collect all these pieces, you get minus 2 gamma nu, gamma beta, gamma alpha, plus gamma beta, gamma alpha, gamma nu, plus gamma beta, gamma alpha, gamma nu, so I have a 2 here. Okay, so I have got to this point. Remember, I'm just checking this right-hand side here using this solution. Okay, now I have got to that point. I have to cancel, otherwise I don't know where to write, and so. Okay, now in these things, let's use the anti-commutation rule on these and these. If you do, so let's take these now. Let's bring it here. I have 2 gamma beta, gamma nu minus 4 g mu beta. All this is multiplied by gamma alpha plus 2 gamma beta, gamma nu, gamma alpha plus 2 g nu alpha. So I have used for these two the commutation relation, gamma nu, gamma beta, and so I get gamma beta, gamma nu, but then I have to be careful because there is a minus, and so the minus and minus gets a plus, there is a 2, and I have the 2, and then I have the 2g beta, but now with a minus sign, so I get minus 4. The same on the other side. For these things, I keep gamma beta, and I anti-commute gamma alpha and gamma beta according to those rules, and I get this expression. Well, it's easy to see this piece and this piece are the same, but with a difference in sign. So what you are left is minus 4 g nu beta gamma alpha plus 4 g nu alpha gamma beta. And remember then, this was just this piece, okay, but we never put in the I over 2, so I have to put in the I over 2. There, I inserted just this piece, the commutator, never the I over 2. So I have to multiply this by I over 2. And if you multiply this by I over 2, you get exactly this. Okay? So this is the proof that this is the solution, not the proof. This is the checking out of the fact that this solves this equation. It's possible to prove that is also the only solution, modulo unitary transformation. So now that we have the reason I wrote down on the blackboard all the steps is because I want that you go through all the steps. You will never be asked in an exam to work out all the steps, but you know, if you go through all the steps, you develop that kind of, you do that kind of gymnastic that might be very useful for the final exam, okay? Now, did you get the right information of when you will have the tutorial or not? Because, you know, I was decoupled from the tutorial. The head of the whole course is Ranja Daemi, and he gave the tutorial to somebody and to me the course. And so that is why I don't know. I informed the person of the tutorial, but he was in Cambridge, and it was a mistake of the secretary to put the tutorial last Friday. He had told her that he would not be here, but. Okay, so now that we have this form, we can write down the expression of this. Now we have this form, so we have the explicit form of sigma. So we know the S. The S we insert in the gamma, and we have that S of A, but A is equal I plus delta omega mu nu. This is equal to the identity minus plus. We have an I here. There is a 4, there is a 2, so we get an 8. I and I gives minus 1. Then there is a minus, so we get 1 plus 8 gamma nu delta omega mu nu. Okay? So now we have almost everything for this expression. So this is the Mannery transform. We have almost everything. This is the commutator. So this sigma, this train sigma, is not a Pauli matrix, but we will see that it will get close to the Pauli matrices. Is this object here. Okay? If you want, you can call, if you want alpha beta, then you can call alpha beta, and here alpha beta. But this is the expression. What do we have to find? We have to find this. But this is something that has to do with the Lorentz transformation in the space-time. Okay, so let's go and see how it is. Now, let me write down here the things that we need. So we have that S. Okay, so let me write down all we need here. Okay, A mu nu is equals to delta mu nu plus delta omega mu nu. And then we have that S. Let me indicate S of just this object, not A equal, because after all, this is a constant and S is only a function of this. So delta omega AB alpha beta is equal the identity plus 1 over 8 gamma alpha gamma beta delta omega alpha beta. Okay, so we have the transformation in space-time, the A mu, the infinitesimal transformation, and we have the transformation for the wave function. Okay. Now we have to find the omega AB. Let me, what else do we need? No. We can cancel all the rest. Oh, well, of course, we have to remember x prime mu is equal A mu nu x nu, and we have that psi prime x prime is equal S of A psi of x. Okay, this is the space-time transformation, and it goes with this. This is the this is, let me write in a more coherent manner. Let me write here x prime is equal A mu nu x nu, and the infinitesimal transformation we write as delta mu nu plus delta omega mu nu. And then we have, so this is the space-time transformation. The Hilbert space transformation is this. And this, we have found that this SA with A equal the identity let's say delta omega is equal the identity plus 1 over 8 gamma nu delta omega mu nu. Correct? Yes. Okay. So this is the space-time part, and this is the Hilbert space part. Okay? We have almost finished, at least for the infinitesimal transformation, but we have to find what is this parameter. Everything there in order to have some space to work out the things. So the omega, you see, they first enter into the space-time transformation. So let's see what they are. For example, so now examples of delta omega alpha beta or mu nu. Okay, let's make a choice. So for example, we choose something, we implement on the x, and we will see what happens. So let's make the following choice, that we take delta omega 1, 0. Remember, alpha and beta go from 0, 1, 2, 3. Is equal to delta omega 0, 1. And let's suppose this is just a parameter different from 0 that we call delta beta. And all the rest, all the other equals 0. So this is the only element that is different from 0. Okay. Well, first of all, let's start lowering, and let's lower, for example, 1. And this we know is G1 sigma. So I take this and I lower the index 1. Is G1 sigma delta sigma 0. And this is G11 delta omega 1, 0. Why? Because you see, this object has only 1, 0 as element different from 0. Okay? The G11 we know it was minus 1, so this is delta omega 1, 0, and this is delta beta. Okay? This is also equal to delta omega 0, 1, because if you do the change, if you exchange the two indexes, you just change sign because this was antisymmetric. We still have to prove that it was antisymmetric. We will prove. Now let's see, for example, what happened to omega I1. I have G I sigma delta omega sigma 1, and this is 0 because you know, this object, when sigma is I or j, spatial part is 0, but this can only be j, a spatial part, so this is 0. Okay. Where? This one, right, 1 sigma, sigma 0. So up there, where do I have to change? Here, this. Okay. Now let's do, now that we have, so in this case, let's do the transformation. The transformation, remember, was, remember that A mu nu is equal delta mu nu plus delta omega mu nu, and x prime mu is equal A mu nu x nu. So let's put in this expression, and let's see what we get. With this choice, where all the other are 0 except this element, we get x1 ni equal delta nu mu plus, we have only two. Now let's remember, A is this, so we have to use this, but we have only two objects are different from 0. So we get delta omega 1, 0, delta nu 1, delta 1 mu, plus delta omega 0, 1, delta nu 0, delta 1 mu. All these apply to x mu. Why I have this expression? Okay, this object has two indexes. It has to have mu and nu, but I know that I have only one parameter. Okay, so I pull out that parameter that is different from 0, and then I multiply by Dirac delta mu nu, and I know that this object is different from 0 only if nu is 0. Okay, but at least thanks to this, I have managed to put the two index, and I have put the two index mu and nu, and I have put them in a correct manner. Okay, so this delta, this Kronecker delta, is the correct manner to put in the index mu and nu, but remembering that I have only this object. All the other are 0. Okay, so this one now you can write as delta mu minus, let's remember what was the things, delta beta, delta 1 nu, delta mu 0, minus delta beta, delta 0 nu, delta mu nu, and this one is equal x mu. Now let's look at the various components now. That means this is the transformation, this is x prime. Remember that this is x prime is equal that. So I have x prime 0 equal, now I take nu equals 0. So I have x0 minus delta beta x1. And if delta beta, I consider delta v over c, I have x0 minus delta v over c x1. Okay, so I interpret beta as v over c, so delta beta is delta v over c. Then I have x prime 1 is equal minus delta beta x0 plus x1. Put it 1 here, okay, to choose nu equal 1, you have the transformation there, and you get these things. So x1, x1, and this object, and this is nothing else than minus delta v over c x0 plus x1, and then you get that x prime 2 is equal x2 and x prime 3 is equal x3. Why? Because there is this Dirac delta that tells me, look, the index, you have this extra piece only if the index is either 1 or 0, and not if there are other numbers, so you would get the identity, just the identity there. But this transformation, look at this transformation now. Let's look at the things. This is x prime equal x0 minus delta v c x1, and this is x prime 1 equal minus delta v c x0 plus x1. And this is a boost when delta v is very small. When delta v is much smaller than c, this is a boost. There is only the gamma. Remember that this, what is missing to be a boost? This looks like a boost, but what is missing is the factor 1 minus delta v over c squared. But this is second order. This is second order, and second order we have neglected. So basically this is a boost. So what we have found is, look, a boost is characterized by having a delta omega of this form. Now another example. So here we can say, well, boost along x, we have delta omega 1 0 is equal minus delta omega 0 1 is equal minus delta beta. All the other 0. Okay, let's choose another example. Remember, we have to build the omega, so we have to find out this strange parameter delta omega, how they relate to what we know of the Lorentz transformation, because they enter the Lorentz transformation in space-time. Well, another component of the Lorentz transformation is the rotation. Okay, so let me make this choice, delta omega 1 2 minus delta omega, I bring the 2 up, then I change sign, 1 2 equal delta omega 2 1, and let's suppose this is a small parameter delta phi, and all the others delta omega mu nu equals 0. Okay, so the transformation is x prime nu equal delta nu mu plus omega nu mu x mu. And this one, we now plug it in this. Let's remember there is only these two, 1, 2 that is different from 0, but here I have all the indices, so I have to be careful. What I can do is this, plus delta nu 1, delta 2 mu, and then I have delta phi, plus delta nu 2, delta mu 1, minus delta phi. You see, this object is the delta mu nu that satisfies these two things, right? You see, like before, this strange object where I have this delta is basically this is the delta mu that satisfies this property. It doesn't matter if one index is up or another is down, we can pull them up, okay? So this is the parameterization of that object. And you see that is 0 every time mu and nu are different from 1 or 2. They are 0 because this delta gives 0 if they are not equal to 1 and 2. So they satisfy this. When they are equal to 1 and 2, they satisfy this condition. Okay, so this is a manner to parameterize the delta omega. Okay, let's go and look at in components. If we look in components here, we have x prime 0 equal x0. Then x prime 1, let's put 1, 1, 1, and let's see what happens. We get x1 plus delta phi x2. Then we have x prime 2. This is minus delta phi x1 plus x2. And x prime 3 is equal x3. This is exactly a rotation around the axis x3, right? This is exactly an infinitesimal rotation around the axis x3. Means basically this is the infinitesimal version of the following transformation: x1 equal x1 cos theta, cos phi, plus x2 sine phi, and x prime 2 is equal minus x1 sine phi plus x2 cosine phi. Okay, the infinitesimal version of that is this one. So we have found the rotation along x3 over the parameter rotation along x3. The parameters are delta omega 2, 1 is equal to minus delta omega 1, 2, and is equal to delta phi. Okay, so we have found examples. Remember that that was what we needed. Here now in the expression, the goal is to find which is the matrix with which the element in Hilbert space transform, and the only things that is needed is the delta omega, so we have found which is the form of the delta omega. Okay, so basically for infinitesimal transformation we are done. This is how is the things for infinitesimal transformation. Well, let's now go on and do it for finite transformation. That means we have to combine many infinitesimal one and get a finite transformation. So from infinitesimal to finite transformation. That means now we will really determine from S of delta omega, we will go to a S of A where A is finite. let's remember the form. We have everything written there, that S of delta omega mu nu was I minus I over 4 sigma mu nu, or well, actually, let's write already, plus 1/8 gamma mu delta omega mu nu. Okay. Now, we will do now several of these, an infinite set of infinitesimal to get a finite. But let me make an hypothesis. Let's suppose that our delta omega nu mu depends only on one parameter, like in these two cases. And for example, the delta phi was a rotation along x3. The delta beta was a boost along one direction. So let's suppose there is just one parameter. Let's call that delta omega. And then there will be a matrix that we will indicate in this manner. Okay, just one parameter. Then if there is one parameter, whatever, we know this is a matrix in mu and nu. This, differently from sigma, is a matrix in mu and nu. Sigma, that was this object, this commutator, our matrices mu and nu does not indicate the index of the matrix, but indicate which matrix we are studying, okay? Now, we make the hypothesis that this transformation only depends on one parameter, then we can pull out of the matrix. This will be just a set of numbers, okay? There is just one parameter, so for sure we'll be able to pull it out. This is a delta omega that is one parameter, like in these two cases. And this will be what I indicated, I(n). N is somehow the direction. For example, in the case of the boost is the x1, and so on. But this is a 4x4 matrix, where these are the index. So this is the ansatz we will make. And then if you want to bring there, you just pull up the mu using the matrix. Okay, so for example, let's find out how it is this. Let's, for example, for the case of the boost, for the boost along x1, let's find out this matrix, what it is. Okay, in the case of the boost, we have delta nu mu equal delta nu mu plus delta omega I(n) nu mu, but how was it? Sorry, the other way around. Let's remember I canceled it before, but how was it? It was delta nu mu minus delta beta, delta mu nu, delta mu 0 plus delta 0 nu, delta mu 1. Okay, this was the boost. It had this form. So this is the parameter, and this is the matrix then. So the matrix I(n) for the boost, nu mu, is this object. We take the minus, so it's minus delta nu 1, delta 0 mu, plus delta nu 0, delta 1 mu. And this is a matrix that is 0, minus 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? So this is an example of that kind of matrix. This for the boost was this. Now, it's easy to see that, for example, if you do this I(n) twice, you get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, and if you do 3 times, you get again I(n). Okay, so let's see if we do now a set of infinite transformation, but a finite one. So let's suppose we do an infinite set of infinitesimal transformation. Then we have that x prime nu is equal to the limit of n going to infinity of a product of infinite transformation, 1 plus omega I, omega is this parameter, delta omega, I n nu 1, then I have another one, I plus delta omega I, oh, sorry, this is n, not I, n, and this is nu 1, nu 2, and so on, till the last one, 1 plus delta omega, here I have In, and the relative index, but anyhow, these are n infinitesimal transformation, okay? And this is, and then I have to apply this to this is my matrix that now the overall index of this will be ni, and here there is a mu, so this is x mu, okay? This is mu n minus 1. Okay, so I have done, this is a finite transformation in X. Let's see what we get. Well, this is nothing else than the exponential. So you get exponential delta omega In. This is a huge matrix called nu mu x mu. But let's remember that when I have one I, now this is the series of, I have to expand this, and I get I n to the first power, I n to the second power, and so on. But the second power is just this, and the first power is this, but the third power come back to be this. So that means many of these will be the same. So let's do it, and you get cosine hyperbolic of omega In, delta omega In, plus sine hyperbolic delta omega In, all these as index mu x mu. But now we know this feature, and then here is easy to see the following. Let's remember these things, that In square is 1, 1, all the rest is 0, and that In cube is equal to In. Then now let's expand these. Let's expand these. So let's go here. Then if you do, you get the following things. 1 plus delta omega In over 2 d square. This is for the cosine hyperbolic. And so on, plus, and then you have the sine hyperbolic, delta omega In, 1 plus delta omega In cube, 3 factorial plus, and so on, ni mu x mu. Okay, so I am just expanding this, but remember, this one is something that is different from 0, and is a different matrix that is written here. Is a matrix that is 1, 1, and then the first two elements on the diagonal is 1, all the rest is 0. So, and then when you do the fourth, remember you have the cube, but the cube is like the first one and then another one. So you can pull out, and what you get of this result is the following: the identity minus In square plus cosine hyperbolic of cosine hyperbolic of delta omega plus in square plus sine hyperbolic of delta omega in, all these nu mu x mu, okay? Now, if you work out in component, remember in the form of this, I have the form, the explicit form of this, of the in square, and I have the form of in that is here. So if you work that out in detail, you get the following things. So let's plug in explicitly the matrices, and what we get is, so if we plug in the explicit expression of the matrix, we get x0 prime, x1 prime, x2 prime, x3 prime. Remember, this was, we are doing the transformation, sorry, I canceled. But these matrices now become nothing else than cosine hyperbolic delta omega minus sine hyperbolic delta omega, 0, 0. Then I have minus sine hyperbolic delta omega, cosine hyperbolic delta omega, 0, 0. Then I have 1, 1, and all the rest is 0, applied on x1, x0, sorry, x1, x2, and x3. So you get the usual transformation for the boost, right? And if delta omega is the one that you know about delta beta. Okay. So we have seen the manner to get the finite transformation from infinitesimal 1, and everything works, but only for the space-time. Now we have to obtain the same for the S. That was our goal. We want to obtain the same finite transformation, the finite transformation for the S. Okay, so let me cancel here. Okay. Yes. Yes, please. Stop me. Okay, I just repeat the logic, okay? Then the detail you can work out by yourself. No, please stop me because, you know. We have, let me rewind from the beginning so that you have an idea. Okay, we have this transformation on space-time, and we wanted to find which is the transformation of the wave function. Okay, that means the solution of the Dirac equation. And we have found that S has to satisfy some relation. We work out that relation, and the result is this. The next step is we have to find which is this infinitesimal transformation that enter into the space-time transformation of the Lorentz. And for example, we have found out for the boost, those coefficients are exactly, for the boost along x is delta beta, for the rotation along x3 is just these things. The next thing is that, okay, these are infinitesimal transformation. How we can get finite transformation? So we made the infinite product of many infinitesimal transformation. Making that, we realize also that both in this case and in this case, but we analyze this case, this matrix is a very simple matrix because it's that only few elements that are different from 0. So when you do the square, you get the same. When you do the cube, you get the same as the original things. And using this kind of identity somehow, because this is a very simple thing, we found that the finite transformation for a boost is the usual cosine hyperbolic, sine hyperbolic, okay? We can do the same for this one. Now, what I want to do is I want to do the finite, this is the infinitesimal transformation. I want to do the finite transformation also for S. What we can do, you know, we could reserve the last two lectures of the last week to review material. So before, instead of going too further on with the program, the 24th and 26th, you have to tell me, you tell somebody to which part you want me to review, okay? But do it a few days, I mean, don't tell me on the spot because then I have to prepare myself. So let's say before that week, you talk among yourself and tell somebody that send a mail to me or come to my office and tell, we would like that you review this and that. Remember, we have 3 hours. In those 3 hours, we will review material that is not clear to you, okay? But of course, I have to know in advance which is the material that is not clear, okay? So that I can go and, so that means you have in between now and then just catch up with things. Okay, so now this is the infinitesimal. We want to get the finite one. The finite one will be something that acts on the wave function. And we have seen how it is. We have to do the infinite product, n going to infinity, of the identity minus delta omega over, there was a 4 there, n, then we have the sigma mu nu, then we have our delta omega a mu, but that was written in this manner with some matrix mu nu. I take the m power of this and I apply to psi of x. Is it clear why this is a finite transformation? This is an infinitesimal one. I do n times that infinitesimal and I hope to get a finite one. This In is the same matrix as before because this object plus, sorry, this object is the delta omega mu nu, this one. Okay, forget about these things. It's the same object that we had before, and I decided to do a very simple example in which there is only one parameter. But okay, this is the finite transformation. So let's work out the detail of this finite transformation. And okay, first of all, we know that the sigma mu nu is I gamma nu over 2, okay? That is the same as saying that gamma nu is equal minus 2I sigma mu nu, okay? And that delta omega mu nu is equal to one parameter delta omega In, this is some matrix mu nu, okay? Well, then it is easy to see that this object is nothing else than exponential minus I4 delta omega sigma mu nu In mu nu psi of x. Okay, so look what happened. These are 4x4 matrices, and how many you have of them? You have 16. Because they are labeled, not the elements, the matrix are labeled by these two index. This is a 4x4 matrix, and these index are these. So that means here I put, you know, there is an association between element of a matrix, that is this. These are really index of the element of the matrix, and these are the index of the element of which matrix you use. Please. From here to here. This is the definition of an exponential. Yeah, the limit of, you know, when you do x over n times n, you get the exponential. When you do the limit of this times n that goes to infinity, I don't remember here the sign, but this is something like that. Okay, that is why you get the exponential. So Let's, for example, work out this case, in which there is only delta omega 1, 0 and delta. So we have, for example, for the boost we have exponential minus I4 delta beta, because this becomes delta beta. Then I have sigma 0, 1 times IN01 plus sigma 1, 0 IN01. Okay, am I right? Yes. So I have to take and this and apply on psi of x. Let's remember I cancel all these matrices where this matrix IN, and this is the element 0, 1, and this is the element 0, 1, were such that basically these, if you go and so the matrix was the number plus 1, and this was the number minus 1. Remember, this is, of this matrix, is the element 1, 0. We work out before those matrices, and that number is minus 1, and this number is plus 1. Then you have this sigma. And the sigma, you know how they are, because first of all, they are antisymmetric, and second, they are gamma mu, here. So that sigma are gamma 0, gamma 1, okay, and we have sigma 0, 1 is equal minus sigma 1, 0, so we use that fact. We use the fact that this is this, and this is gamma 1, gamma 0, I/2, okay, so you put in all that things, and the net result of this is psi prime x prime is equal exponential minus I/2 delta beta sigma 0, 1 psi of x, and sigma 0, 1 of psi of x is that one. Okay, so that means the finite transformation sigma 0, 1, there is an I, so and another 2, so there is a 4, and this there is a thing, so is gamma 0, gamma 1 commutator psi of x. Okay, so this is all Hilbert space state transform. I lost some I think. Okay. As usual, I lost some eye. Now let's do this other case. And first we will do in space-time the finite transformation, and then we will do in Hilbert space. So let's do the rotation, that is something very common. Any question here? Unfortunately, there is this small blackboard that I have to continuously cancel, because otherwise I don't know what to write. But okay, we managed to build this transformation and for the boost. Now let's do for the rotation. For the rotation, you remember the rotation, what is the crucial ingredient here? Is to get this delta omega and mu, and delta omega and mu, the infinitesimal one, we wrote as delta omega times some matrix mu. Okay? So, for example, let's write the rotation. The rotation was x prime 0 equal x0, x prime 1 equal x1 plus delta phi x2, x prime 2 is equal minus delta phi x1 plus x2 and delta x prime 3 is equal x3. Now this is nothing else than x prime mu equal a mu x mu, but this is the same as delta mu plus delta omega mu on delta x mu, and this is nothing else. Now if you look at this object, you can write this delta mu plus or minus delta phi times I n mu. Now for this, you see, so this is a 4x4 matrix and it's all one. Then there is this extra piece, so it's easy. Comparing this with this form, it's easy to find out that In mu for the rotation is 0, 0, 0, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 0. Okay? So I compare this with the abstract form that is this. Then comparing this with this, you get which is the form of this matrix, and the form of this matrix is this. Okay, now that we have the In, it's easy to see the transformation on the Hilbert scale. The transformation is exponential, minus I over 4, delta phi, that was the angle, sigma mu, I, n, mu, psi of x, and which element were different from 0? You see, the 2, 1 were different from the identity. So this becomes exponential, minus I4, delta phi, sigma 1, 2, I 1, 2, plus sigma 2, 1, I 2, 1, psi of x. Okay? So I have saturated only the index that are different from 0. But which index are different from 0, different from the identity in this matrix? In this matrix, there are only these two indexes, 2, 1 and 1, 2, that are different from 0. Okay, remember, it's 0, 1, 2, 3 as index. So you get that expression, and now if you work it out, you get exponential I over 2 delta phi sigma 1, 2 psi of x. But let's go and see what is sigma 1, 2. Sigma 1, 2 is, from the definition, it is I over 2 gamma 1 gamma 2. Let's work that out in detail. We know gamma 1 and gamma 2 what they are, so I have 1, I have to do the commutator, and the sigma 1 is 0, the Pauli matrix sigma 1, 0, then the other is sigma 2, minus sigma 2, 0, minus, 0, sigma 2, minus sigma 2, 0, 0, sigma 1, minus sigma 1, 0, 0. If you work out this, you get, remember the commutation relation from here, you get minus sigma 1, sigma 2, but let's do it. We get minus I over 2, sigma 1, sigma 2, minus sigma 2, sigma 1, 0, 0, sigma 1, sigma 2, minus sigma 2, sigma 1, and this is minus I over 2, well actually this is related to 2I sigma 3, so it cancels, all the term cancel, you have an I, it becomes a plus, and this becomes sigma 3, 0, 0, sigma 3. So this rotation is nothing else than I over 2 delta phi sigma 3 is the 4x4 matrix applied on this. So this is the 4x4 matrix applied on the 4x4 vector. Now you understand why, now it's easy to understand. Now it's easy to understand why they call this Dirac spin-off. Because you see, you have the sigma matrices. If you take just, let's take the upper components. If we take the upper components, they transform in this manner. So you see, they transform as spin-offs in the sense that you have to do 4 pi to get back to the same angle, right? So that is why the psi, the wave function of the Dirac equation, we have seen the relativistic limit that they correspond to spin 1/2, and now from the transformation you see why they are called spin-off. They are called spin-off because, like for a spinning particle, you have to do 4 pi because of this factor 2 to get back to the same wave function, okay? That is the reason why it is called spin-offs. And if you want to have observables, observables are only function of a couple of spin-offs. That means if you want to have an observable depends on always on product of two spin-offs, because you know, if you do 2 pi rotation and you do 2 pi rotation, you get to the minus these and minus these. Then if you had only one as observable, you would not get back to the same observable doing a 2 pi rotation. But you get back, if you do a 2 pi on this and a 2 pi on this same sign, but also this same sign. So if the observable are a pair of spin-offs, you get that after 2 pi you get back to the same observable. So it's only the wave function that after 2 pi you don't get back to the same things. Let's stop here because there is enough material to swallow for you during the weekend. So let's do that. You collect whatever you have not understood, and a few days before the 24 you let me know. Review this, review that. If you don't tell me anything, then I will review whatever I think it might be most difficult for you, but I would prefer that you tell me. And of course, remember, I mean, the last week we will have only 1 hour and a half and 1 hour and a half, so 3 hours. So, I mean, don't ask me to review the whole course in 3 hours. Just pick up some points that you have difficulty in understanding, and then this one I can review. So we will do some new material only next week, and then the week after only review, okay?